Voltage contour maps, or equipotential lines, using Excel. This example shows two equal and opposite charges spaced out on the x-axis. We have a plus q at the point minus a, 0, and a charge minus q at plus a, comma 0. Now a will be 100 when we work in Excel, but the general field point, xy, is also shown, and we can calculate the volts at the field point by the superposition of Coulomb potentials kq over r. So I show the kq over r1 and the k minus q over r2. And if we factor out the k, which is the Coulomb constant, and q, and possibly a scale factor for r if we were working in centimeters or inches, and if we just want to work in units, whatever scale factor might factor out, that all factors out as a constant c. And what remains in the curly brackets then for the potential is 1 over r in each case, right? Where r is, from the distance formula, the square root of y minus y0 squared plus x minus x0 squared. Now y0 is 0 for both of the charges. X0 for the charge on the left is minus 100, right? It says minus a, but a is 100 when we work in Excel, so minus 100. And the second term in the volts formula, the x0 is 100. So with a range of cells where x and y go from minus 100 to 100, we'll start filling this in by the Coulomb potential. So 1 over square root of y squared plus x minus 100, or x plus 100 squared, which represents 1 over r for the positive charge. And now let's include the negative charge, minus 1 over the square root of y squared plus x minus 100 squared. And there. Now notice I said y and x, but I entered cells with dollar signs and A's and numbers, right? So I just want to go through the idea of absolute cell references, right? So column A represents y. So I'm in cell B2, where y equals 100 and x equals minus 100. So when I said y squared, I entered $A2 squared. And the dollar is, in Excel, referred to as an absolute cell reference. $A and a 2 means that the $A should never change when this formula is copy-pasted to other cells. Similarly, x values are in row 1. So here I am in cell B2, and when I wanted to refer to x, I typed $1. And that the dollar sign in front of the 1 means that the 1 is absolute. If I were to copy-paste this formula to other cells, the 1 would never change. So to demonstrate, I'll copy the formula that was entered in B2 down to C7. And you'll see that the reference where I said y, which when entered in cell B2 was $A2. Now that it's pasted into C7, it became $A7. So the idea of an absolute cell reference is $A means the A shouldn't change. So even though the formula was pasted one column over and several rows down, only the row changed. 2 went to 7, but A stayed the same. Similarly, for the x values, which are stored in row 1, when the formula I entered in B2 referred to x, it referred to $1. And now that this has been pasted over and down to C7, B went to C, but 1 stayed the same. So the reference for x now is $1. So with the formula shown in the formula bar, you see the y value 95 and x value minus 99 is correct. In any case, to finish the formula, I want to have that scale factor, which I called C earlier, but this is going to be kept in cell A1, which I want absolute, right? So $A, $1. And I'm just showing the effect of changing it. 6,000 gives us like around 30-something volts. Let me copy that formula now and paste it in the entire field. I had a 1 as a placeholder at the end so I didn't get lost. There. So that's a field of cells that represents the superposition of Coulomb potentials for the two charges at all x values and y values between minus 100 to 100. Now for the contours. I have another range of cells, but up here I have a place to put the equipotential value I want to see, 15 volts, and delta is like a tolerance, so within half a volt. And in this field of cells that has a border, I'm basically going to say if the value I calculated minus the reference value, 15, that I want to see, if that is within the tolerance, so less than the tolerance, I want to show a 1, otherwise a 0. Right? So if I copy that formula and paste it through the entire field that I have a border around it, so I saw where I was, I get mostly zeros, but I have ones wherever I was within a half a volt of 15 volts, and that's the equipotential or contour I wanted to see. Now, to highlight that, I'll just use the conditional formatting in Excel. So I highlight all the cells and go to conditional formatting, and I want the equal to, right? So if any of those cells highlighted equals 1, it's going to show up as red, and I can customize that as needed. So all my 1s now are red. And I think you're starting to get the idea. Now the trick is to take all those cells and reduce the size to something small. Like I'm going to try, let's try 3 pixels. And let's also then highlight the rows that form the box that I want and make those 3 pixels. There we go. And now just to make this a little easier, I'll turn off the grid lines and the headings and the formulas. And I think you get the idea. I get a graph without graphing, just using conditional formatting. I can look for the 20-volt line. I could look for a 30-volt line. I could look at the 0-volt line. I can decide that was too thick, make the tolerance 0.2 instead of 0.3. Here's a 30-volt line again. Let's make the tolerance 1, so you see a thicker line, etc. Right? Here's minus 20 volts. So I can play around with that as needed. And if I wanted to, I could have a set of volts that I want to display equipotential lines. So what I've done here is I have an animation that basically has a loop that increments the volts I want to see from negative values to positive values. I'm also showing the Excel formula that I used here. And here's 4 charges. I think I used 75 units from the origin in both X and Y to locate the positive and negative charges. In this example, I have a negative charge on the positive x-axis and a conducting plane on the negative x-axis. And I'm using the method of images, which allows us to calculate the volts at the field point as the superposition of Coulomb potentials from the minus charge and an image charge, which is not unlike a reflection in the mirror. And I come up with this idea that the image charge is the same distance from the conducting plane as is the negative charge, but on the opposite side. And here's the animation and the Excel formula. In this last example, we have a uniform field created by parallel plates with equal and opposite surface charge densities, positive sigma on the left plate, negative sigma on the right. Remember, the electric field then is sigma over epsilon zero, so I call that E0, and that is a constant uniform field from left to right. Now, with a conducting cylinder at the center, we cannot use Coulomb potentials to find the volts at the field point, but I'll include a reference in the description that shows how I can use the formula where it says with neutral conducting cylinder. In that formula, we have minus E0, which is that constant uniform field. We have X, and 1 minus a ratio squared, which is capital R, the radius of the cylinder, not identified in the figure, and little r, the distance from the origin to the field point. Now, if we were actually doing this and taking measurements in lab, we would probably have two conducting planes with the conducting cylinder in the center. So our constant uniform field would be found by volts over distance. And with the circuit shown with two voltage sources with the center point grounded, that would give me positive delta V on the left, negative delta V on the right, a total of 2 delta V across the plates divided by 2A, with A shown as from origin to one plate. In other words, I get delta V over A as the uniform electric field. Now, with conductors, instead of a uniform density, the formula that I showed earlier, and now is shown where it says with grounded conducting cylinder, that formula is now approximate. It is a better formula when A is much larger than the radius of the cylinder. And real quick, with a scale factor set up to be such that I would have expected 50 volts, where X is minus 100, I'm getting about 48 and change. In any case, here's the animation and the Excel formula. And that's it. Voltage contour maps or equipotential lines using, surprisingly, conditional formatting in Excel.